Let's get started with physics. UML's Wi-Fi doesn't seem to be working, so good luck with the clicker. Basically, the clicker is not going to work, so Wi-Fi works in this room. Okay, so let's get actual physics started, which is going to be a really exciting start. We're going to be talking about walking in a straight line, or moving in a straight line, for the rest of this week. Right, let's start with a clicker question, which you will answer without any clickers. So, the way you answer this is by a show of hands. So, get ready to exercise. So that's a map from the ICC, which is somewhere near downtown. Only. And you're told that the distance is approximately 2.5 kilometers. And your average speed is 5 kilometers per hour. And I'm asking you a relatively straightforward question. How long would it take you to walk that distance with that average speed? Okay, show of hands for like C. Right, you're all waiting, at least some of you are, and you got the right answer. The rest of you did something wrong. You divide the total distance by the total average speed, and you get the average time. Right, so the answer is 30 minutes. As an FYI, for those of you who are looking at the slides online while I'm lecturing, the online slides do not have the answers yet. Right, all clicker question answers will be like you will tell me during lectures, and then after lectures, when I update the slide, the clicker answers will go. Okay. So motion in a straight line sounds relatively straightforward, and that's kind of why we choose this to start with. We're going to start defining terms. Okay, the first term that we want to get familiar with is displacement. Displacement is commonly mixed up with distance. So distance is the total length traveled. Displacement is by definition just a change in position. Okay, so if you have some initial position x1 and some final position x2, then the displacement, which is delta x, where delta basically stands for a difference, is x2 minus x1. I'm going to get back to the swimmer example in a second. But there is a difference between displacement and distance. Your car is a dormitory. Let's say you pull out your car every morning, come to school like a good kid, and go back home like a good kid. Your car has actually traveled a certain distance, right? It's gone to school and gone all the way back. What is the actual displacement of your car? Zero, right? It started in the garage and ended up in the garage. Right? Displacement being a change in position is zero. So one thing that displacement cares about is just change in position. The other thing is your direction. Obviously, if displacement is zero, there is no sense in saying direction of displacement. Zero has no direction. But let's say that you have a swimmer, right? And let's say that they start at some initial position, which I'm calling x0 is 0. Now, motion in a straight line, you have two options. You go that way or that way, right? Along the line, you only have two directions that you can go in, right? So if I call one direction positive, the other direction is automatically negative. Does that make sense? And it's your choice, right? That convention of which direction is positive is totally up to you. You get to choose, right? But once you choose that going that way is positive, then going the other way is automatically negative. Okay? So let's say that this swimmer starts out, and I'm going to take to the right as positive and to the left as negative, and then this person goes for a little swim. They go 4 meters in one direction, right? And then they go 5 meters in the other direction. So that's what they did. What is the total distance that this person swam? Not 9. is 13. The total displacement, on the other hand, is anyone. What's the displacement of this film? -5. Right? And that minus is telling you something, right? The distance, it doesn't tell you anything. Right? This person swam 30 meters, but they're 5 meters away from where they started. Right? So that distance information is kind of useless, right? It's not telling you where they are. Right? But the displacement information is telling you where they are with respect to where they started. Right? They are 5 meters behind where they started. They're 5 meters in the negative direction with respect to where they started. Does that make sense? That's what displacement is telling you. And this choice of coordinate system, right? This choice of what I call 0 is completely up to me. If I chose a different 0, right? Like if I chose that to be 0, right? Then this person started with an initial position of +5. Right? So their displacement at the end of that motion is still -5. Does that make sense? Right? My changing my coordinate system doesn't change my actual displacement. Right? And if displacement is what I'm bothered with, all I'm looking at is where I started and where I stopped. Everyone good with me so far? Okay. Now, we can define something called an average velocity. I'm going to talk about velocity for a quick second. The terms velocity and speed are commonly mixed up in nature, right? Physicists, like me, like to be fussy and precise about what those words mean. Okay? Speed is a measure of how fast something is moving. The average speed is the total distance over the total time. Right? Velocity, on the other hand, is a measure of how fast it's moving and in what direction it's moving. Right? So your car speedometer, for example, measures the speed. Right? It doesn't, when I'm reversing, my car speedometer doesn't go there. Does that make sense? It means it's not measuring velocity. Right? Because there is a difference, as anyone who's been in the car will tell you, between driving forward and driving backwards. Right? So as far as velocity is concerned, these are two different velocities. But as you drive forward at 5 miles an hour, drive backward at 5 miles an hour. Right? Nice speeds. In terms of speed, no difference. So when we're talking averages, first off, it's an average over a certain amount of time, right? Delta x being the displacement in that amount of time, delta t being the amount of time for that displacement. So average velocity is total displacement in that delta t divided by that time delta t. Right? If I was looking for average speed, it would be total distance traveled at that time versus delta t. Right? So if we go back to that swimmer for a quick second, whose displacement was -5, distance was 13. Let's say that they did that in like 3 minutes, like 2 minutes. Okay? So then the average speed is that 13 divided by 120x. Right? But the average velocity is -5 divided by 1. Right? Velocity bothers with displacement. Okay. So typically speed is always taken to be positive. It's not telling you anything about direction. As we go into more dimensions than just a straight line, I'll be using the term velocity a lot. And it's always displacement over time. Okay? Speed is the magnitude of the velocity. So when I say something is moving with a certain speed in a certain direction, right, I'm defining its velocity. It's instantaneous velocity, like the magnitude of velocity, just the size of it, is the speed. Right? That's the instantaneous speed of the object. Everyone good with me so far? Like relating velocity and speed. So as a question, if one would ask you to find the velocity of something, you give a magnitude and a direction. Right? If as a question one asks you to find the speed, you just give a magnitude. Okay? Right. Fun with graphs. So you can plot. Now remember, we're talking about motion along a straight line right now, and just to keep things simple, it's going to be motion along a horizontal straight line. Okay? So if I plot the position of something as a function of time, right? If its position as a function of time is changing, that thing is moving. Right? If I were to plot the position versus time of something which is not moving, right? So that's x, that's position, that's t, right? And if I plot a position versus time graph that looks like that, that means that thing is not moving. Right? Not very good. However, if it's moving equal intervals of distance and equal intervals of time, right? What you get is a graph that looks like this. Right? So it's moving equal distances in equal amounts of time, which means it's moving with a constant speed. Right? That's your constant velocity. Right? Its direction isn't changing. In every equal interval of time, it is taking an equal distance forward. Right? So its velocity during this motion is not changing. Right? So the position versus time graph of an object moving at a constant velocity will look like a straight line. Right? And the slope of this straight line, which is that ratio, that rise over run, right? So that's the amount of time, that's the distance traveled. That slope, delta x over delta t, is the velocity, right? By definition. So velocity is delta x over delta t, or the slope of the position versus time graph. Okay? As that slope changes, you can have different velocities, right? So these are three different objects, right? The red object has a negative velocity, right? That's not saying it's moving slower than the blue or the rocky purple, right? It just means it's moving in this direction, right? Plus and minus are directions along a straight line, right? A positive velocity indicates you're moving in the positive direction. That makes sense? A negative velocity indicates you're moving in the opposite direction. Okay? The magnitude of the slope itself is what tells you which one is moving faster. Right? So if you look at the blue one and the purple one, right, they're both moving in the same direction, both plus these. Right? But the purple one has a higher slope. Means it's moving faster. Right? In the same amount of time delta t, it's going a larger distance. Everyone with me so far? Okay. So velocity is a rate of change graph. Okay? Before we get to instantaneous velocities, let's just discuss that concept a little bit in more detail. It's a rate of change graph, and rate of change graphs are easily misunderstood. Right? What that v versus t is telling you is how fast something is moving as a function of time. And if I were to plot velocity versus time with this, it would look like a straight line. Everyone with me so far? What I'm saying is, if I have an object, right, and its position versus time graph looks like this, right, a nice straight line, right, then the velocity versus time graph for this guy will look like this, right? It's a constant velocity. It's a v that's not changing. Right? So this v versus t graph is the rate of change for the x versus t graph. Okay? A common example for rate of change graphs is something like college tuition. Right? If you were to plot like the average percent increase in college tuition over like the past few decades, right? So that's percent increase in college tuition over like, this is the 2000s, the 10s, and that's kind of where we are. your graph looks something like this. Right? Now, looking at that, one might be tempted to think that college tuition is bad. Right? But that's not what that graph is actually saying. It's saying that the percent increase in the tens was less than the percent increase in the zeros. But it's still a percent increase. Right? So what this graph is telling you is kind of true. College tuition just went up. Right? The rate at which it went up changed. Right? But if you were to start plotting tuition versus year for something like this, right? The tuition, the actual tuition number versus year would still look like that. Still a positive change. Is everyone following me so far? Right? So what a rate of change graph does is it tells you how the slope of another graph is there. Right? So velocity is the slope of the position versus time graph. Right? And if that position versus time graph slope is changing, that means velocity is changing. If the position versus time graph is a straight line, right, which means it has a constant slope, it means velocity is constant. Everyone with me so far? Okay. Right, so now let's talk about instantaneous velocity. So far, when you take a total displacement over a total amount of time, right, you're essentially averaging velocity, right? It's total displacement over total time. So the average velocity over that delta t is what we're finding, right? However, if we bother more with what is the actual velocity at a given instant, right? That can be changed. So this, by the way, was a swimmer, right? So that's the swimmer and they picked up speed, right? So during their motion, their velocity increased. Everyone following me so far? Right? It's like they accelerated during their motion, which of course is what I'm talking about, acceleration. When we typically say the word v, what we're talking about is the instantaneous velocity. Right? It's how fast is something moving at a given instant in time. So graphically, right? So if I have a position versus time graph for an object, and that's what the object is doing. That's how the position versus time for that object is changing. Right? If I talk about the velocity of that object, right, I have to talk about the velocity at a specific point. Right? Because this isn't a straight line. Right? So the velocity during this motion is actually changing. Right? This thing is either speeding up or slowing down. Someone tell me whether this thing is speeding up or slowing down. Why? What's happening to the slope? Slope is decreased. Right? Slope being the velocity, that must be decreased. Everyone follow? So the actual slope at any given point gives you the instantaneous velocity. So you can find a bunch of average velocities, right? Delta x over delta t, but only one, which is the tangent at that point, right, actually gives you the instantaneous velocity at that point. Everyone follow me? Okay, so when you look at a position versus time graph, right, if the slope of that graph is changing, velocity is changing. If that slope is going up, velocity is going up. Right? If that slope is going down, velocity is going down. Right? The magnitude of the slope is the magnitude of velocity. Okay? So, out of all of those, obviously, depending on where you calculate it, you'll get different values. So what we're saying is the tangent is the correct answer. So at any given point, if I'm looking for the instantaneous velocity, right, what I'm looking for is the tangent at that point. Okay, clicker question. And I'm going to actually try using the iClicker. Maybe the internet's back on. You guys can see the question. I'm going to just attempt to log into iClicker and see if I can start a session. Not looking promising. Yep, I still have no Wi-Fi. Okay, you guys have had enough time to look at the question. How many people for A? Anyone for B? Anyone for C? And I have B. And the rest of you are on which answer? Okay, let's try again. Anyone for C? I should see everyone's hand go up, C being the correct option. Okay, so if you read the question, it says that, first off, what should the displacement be? If you just read the question, straight off the bat, what's the displacement? 0, right? So you have to end up where you stop. Correct? You can't go backwards and down, so I'm going to circle back around. Right? But your final position has to be the same as your initial position. There are 2 graphs on this which do that. Right? B and C. So one of those 2 has to be the correct option. Does that make sense? Okay. You're also told that for certain points of time in this, you're staying at rest. Right? At rest is a line parallel to the time axis. Right? So that is your correct response because you stay initially at rest for a little bit of time, then you move at a constant velocity, so that walks slowly in a straight line, stops to rest, and then runs quickly back to their initial position. Everyone with me so far? Right? Time keeps going forward, right? It doesn't stop during any of this. Okay? Right, let's try another one. So all these dots represent is the position of an object at certain periods of time. They're equal intervals of time. So all those dots are tracking the position of an object at equal intervals of time. Which object travels the furthest in a given interval? Red, green, or blue? Green, right? Right? Which means that that's the one that's moving fastest. So it has the greatest speed. Right? Greater speed implies greater distance in the same amount of time. Right? All these dots are separated by equal amounts of time. Right? So whichever ones are the furthest spaced are the ones that are moving fastest. Like that's the object that's moving fastest. Okay. Now let's start talking about acceleration. So, velocity is the rate at which the displacement of an object changes. Right? On a normal motion, the velocity of an object can change. Right? Like when I drive to work, my car is initially at rest. Right? It picks up to some nice comfortable 26 speed on my way to work. Right? And then it's at rest again to the velocity. Correct? So during its entire motion, its velocity can change. Right? Acceleration is that rate of change in velocity. So just like v is defined as delta x over delta t, acceleration is defined as delta v over delta t. Right? It's the rate at which velocity changes. Okay? In day-to-day language, people use 2 terms, acceleration and deceleration. Right? Indicating whether you're picking up speed or losing speed. In physics, we use one word, acceleration, and it implies velocity change. It doesn't say anything about whether velocity is increasing or decreasing. change, delta v is 0, meaning acceleration is 0. Right? If delta v is greater than 0, right, it implies acceleration is positive. But that does not imply that the object is moving fast. Okay? So, remember, it's delta v over delta v. So, let's think of a slightly more complicated example. We started by saying that way is positive and that way is negative. Right? Let's say I have an object moving in that direction with increasing speed. Correct? Like you can go in the negative direction and increase speed. Right? So what's happening there is at some instant, let's say this thing's speed was like minus 10 meters per second, indicating you're going 10 meters per second that way. Right? Some instant of time later, speed is now 15 meters per second that way. Right? So its new speed, new velocity so to speak, is minus 15 meters per second. Right? Minus 15 minus 10 means that its velocity changed by minus 5. Correct? Which means its acceleration is negative because delta v is negative. Right? So what we just described is a situation where you're moving in the negative direction and picking up speed implies a is positive. A is negative. Right? So there is no link that if acceleration is positive, that implies the object is picking up speed, and if acceleration is negative, that implies the object is losing speed. That's not true. Right? The positive and negative on acceleration are just dependent on what directions you guys picked as positive and negative. This makes sense? Okay. There is a relation that you want to bear in mind. If you think of these directions as positive and negative, right? So positive and negative. If v, the velocity points in a given direction, and if a points in that same direction, right? If velocity and acceleration both point in the same direction, the speed of that object will increase. If velocity and acceleration both point in opposite directions, right? One's going this way, the other's going that way, the speed of that object will decrease. Right? So a negative velocity with a positive acceleration is a slowing down. A positive velocity with a negative acceleration is a slowing down. Right? A negative velocity with a negative acceleration is a speeding up. This makes sense? Okay. If you forget everything else about today's lecture, remember that. Right? If A and B point in the same direction, right, that thing is speeding up. If A and B point in opposite directions, that thing is slowing down. Okay? Now, again, since acceleration is defined as delta v over delta t, if I plot velocity versus time, right, the slope of this graph is the acceleration. So this is now an object that's moving with a non-constant velocity. Right? If you look at v versus t, that graph is not horizontal. Right? So at different instants of time, this object has different velocities, which means it has a non-zero acceleration. Right? This velocity versus time graph is a straight line, right? Indicating that its velocity is increasing by equal amounts of time. Right? It's not saying that it's doing equal distances in equal amounts of time. It's saying that it's increasing its velocity by equal amounts in equal amounts of time. This makes sense? So as you go further out in time, this thing is moving faster. Right? So its acceleration, which is the slope of this, is a nice positive constant. Does everyone see that? Right? If I plot the slope of that line, it's a nice horizontal line. Right? However, if I want to talk about the position versus time graph corresponding to this, right? So now I'm looking to see how the position versus time of an object whose velocity versus time looks like that. Its x versus t graph will look like this. It's parabolic. Right? What this is telling you is that in equal amounts of time, this thing is traveling greater and greater distances. Right? Indicating its So the V versus T for this is this, and the A versus T for this is just this. Does that make sense? Right? This is the slope of this guy, this is the slope of this guy. Everyone with me so far? Okay. Okay, so you can find A the same way. Now the nice thing is most common motions, by the way, again the same thing, instantaneous acceleration is the instantaneous or the tangent to the V versus T curve. Okay? And a downward slope just implies negative acceleration. Right? Okay, and that's what I was saying earlier. If V and T point in opposite directions, the object is slowing down. Is it possible to have a physical situation in which V is 0 and A is not 0? Can I have an object with 0 instantaneous velocity, right, and a non-zero acceleration? Yes, it's me starting my car. Right? At the instant I start my car up, right, the velocity is 0. It's not going anywhere. Right? I'm pressing the gas, that's what's making it go up to a certain speed. Everyone with me so far? How many controls in your car can actually change the velocity of the car? Can the gas pedal do it? Yes. Can the brakes do it? Yes. Can the steering wheel do it? Yes. It changes direction, right? Correct? Velocity is magnitude and direction. So anytime you have something that can change the magnitude or the direction, you change the velocity. We good so far? Okay. Most common motions can be broken down, at least what we'll start by studying. You can break them down into periods of constant acceleration. Okay? And when you break them down into periods of constant acceleration, you can use the promised math. I did promise you guys math, right? So the big three kinematic equations apply to scenarios where acceleration is constant over a certain amount of time. Caveat before we get to using these, I do not expect you to memorize them. They will be provided on the equation. How you use them is of course totally up to you, and that's what we'll be doing. Okay. First, straight off the bat, you do not need to know how these are derived. They're derived from basic definitions, which are the definitions of velocity and acceleration. Okay? They all talk about the same scenario, which is motion at constant acceleration. Right? So A is changing, and we deal with situations where acceleration is changing later on in the semester. Right? In those situations, these equations do not apply. Right? They apply for amounts of time t over which A is constant or can be assumed constant. Right? So what we're saying is constant is acceleration is constant. Right? And if acceleration is a non-zero constant, V is changing. Right? Since acceleration is the rate at which velocity changes, if acceleration is non-zero, that means velocity is changing. Right? The V subscript zeros are your initial velocities, and the V's without the subscript are your final velocities. Everyone with me so far? Right? Same thing for the displacement. Subscript 0 indicates initial position, and the one without the subscript indicates final position at time. Okay? Now let's look at a simple problem. And this is someone driving who has a certain finite reaction. Right? Let's say you're driving along at a nice constant velocity. Right? And you see something far ahead of you, and you decide to hit the brake. The fact that you have a reaction time indicates that between you seeing something and hitting the brake, there is a time period. during which you did not take a break. Correct? During that time period, your car moves because it hasn't lost. Right? That's your reaction. That's why substances that increase reaction times are dangerous for driving. Right? Because the longer it takes you to react to something, your car is still actually moving forward in that time period. Everyone with me so far? Okay. So if I were to calculate how far away am I from my initial position when I come to a stop, right? How much distance did my car travel? Right? I account for that reaction time, right? That distance traveled, and then the distance over which I slowed down. Everyone following me so far? Okay. If this is my complete motion, is acceleration constant during this entire motion? No, it's not. Right? During my reaction time, there is a zero acceleration. Right? When the brake is pressed, there is a non-zero acceleration. Right? So for this entire motion, I do not have a constant A. So the kinematic equations cannot be used unless I break it down. Right? I can break this down into two periods of constant A. Right? First off, my reaction time is A constant is 0. Right? And second off, the time I'm actually moving, right? Where I have that minus 6 meters per second squared acceleration. Everyone with me so far? Okay, so the way you do such a problem is you lay out what you know and what you do not know. Okay, so this question actually gives you a diagram, which I'm going to try and copy. It says my reaction time is 0.5 seconds. Right, so I travel a certain distance during that. Okay. So this is kind of what I mean, right? During this distance, I traveled with a constant zero acceleration. And during this distance, I traveled with a constant non-zero acceleration. Everyone good so far? The total distance traveled is this guy, which I'll call x1, plus x2. Right? The distance I traveled in my reaction time and the distance I traveled under braking. Okay? Let's first find x1. Since there is no acceleration, right? Position, like change in position is average velocity times time. Right? You can use one of the kinematic equations for this with A equals 0. So I can use x equals x initial plus v initial times t plus 1/2 at squared with A equals 0. Right? For the first reaction time portion of this. So if A is 0, that term goes away. So x is v times t, which is 14 times 0.5. So great, 7 meters. Everyone's with me so far? Right? All I'm saying is during my reaction time, when I did not hit the brakes, my car, which is traveling at 14 meters per second, travels for half a second. Right? So it's covered 7 meters. Okay? Now let's look at the second chunk, right? Where there is a constant non-zero acceleration. Over here. I'm still looking for x2. Right? Do I know my initial velocity? Do I know the velocity the car is moving at when I hit the brakes? That's my initial velocity. Right? Because at the start of that time period, where A is minus 6, the velocity is 14 meters per second. That's how fast the car will move. Right? Do I know the final velocity? 0, right? Presumably I want to brake to a stop, right? So my initial velocity is 14 meters per second. Final velocity is 0 meters per second. Right? And I'm given that I'm looking for x. I do not know how long this second chunk of time took. Everyone with me so far? Okay. So You'll get more familiar with the kinematic equations. I'm going to tell you which one to use here. So we have one which looks like that. Right? It's the one that doesn't have time in it. I know this is 0. So this is minus v0 squared is that. 2 times minus 6 gives me delta x. Solve for x. Everyone with me so far? Right? So you get x2. Right? The total distance traveled is x1 plus x2. Okay? And as you can see, this process can be used to break down most common motion periods of different constant acceleration. Everyone with me? Okay. Let's do graphs. Okay, so let's say that I have an x versus t graph for 4 different objects. This one is asking you which 2 objects are at the same position at the same time. Just looking at it, can you tell me? Which 2 objects are at the same position at the same time? These are position versus time. 2 and 4? 3 and 4. Right? They intersect nicely. That nice little intersection is telling you that at that amount of time, they're at the same position. Right? So, by the way, that's the answer, but are they moving at constant velocity or are any of them experiencing a velocity that changes? All of them have constant velocity. Correct? They're all straight lines in position versus time. Okay, let's go with this one. So that's a position versus time curve, right? And I have a highlighted spot at 3 seconds, and I'm asking you whether the velocity and acceleration at that point are positive or negative. So in order to identify whether velocity is positive, all I'm looking at is the slope of the position versus time graph at that location. Is that slope positive? Right. So velocity is positive. Okay. Acceleration is the rate at which velocity is changing. So what's happening to that slope as time increases? Is it increasing or decreasing? Look at it as time increases. Is it going like this or is it going like this? The slope is going up, right? The slope is increasing. So A must be positive. This makes sense? Right? So in this scenario, both your velocity and your acceleration are positive. Right? So is this thing picking up speed or losing speed? Picking up. Okay. So that's positive for velocity and positive for acceleration. And one last question before I let you go. This is a velocity versus time graph. It's not a position versus time graph. Is this thing moving at constant velocity? No. Right? Its v is actually changing. The question is now asking you for velocity and acceleration at 2 seconds. So is the value of velocity positive or negative at t equals 2 seconds? Negative. So is velocity positive or negative? Right? What about acceleration? Positive. It's the slope of that time. Right? So this is an object at constant acceleration. Okay? And as an FYI, think about what this means for position. Right? V is 0 at 3 seconds. Right? So it changes direction. It went from a negative V to a positive V. Right? So it changed direction. Everyone with me so far? Okay, I will see you guys with working clickers Wednesday at 8 o'clock. 30 seconds. So 5 kilometers is the 2.5 kilometers the distance, right? 5 kilometers per hour is the speed. So if I want to travel, it's 2.5 divided by 5, right? That's half. No, 2.5 divided by 5 is half. Yeah, 0.5 is 30 minutes. So 0.5 hours, right? That's 30 minutes. That makes sense? It wasn't working. Yeah. Not you. Yeah, you can do that. When it works. Huh? Yeah.
On my absence, it says I have 5.
You don't have any absences. It's just me trying to start sessions and.
Thank you.
Huh? You have a visit.
Nice to you.
Hi. Mails happen. This sounds like a tech issue that a few people have had. Just mails happen. There's a tech support link there. Just mail them. You can see. Mails happen. Emails happen.
Emails happen.
Okay. That's a tech issue. So
Okay.
You can CC me on it. Clicker hasn't worked today. I didn't have Wi-Fi, so I tried to start a session. I did start a session, but then I couldn't do anything with the session, so it was a mess.
Okay, and for this app, so when I go to the digital command, it's usually 5 options. Would I
It's up to you.
Oh.
They all come with SAP and Plus.
Oh.
The variation is 1 semester versus 2 semesters, and whether or not you need a hard copy textbook. You don't have any. It's just the clicker is not fixed.
Oh, what about the
When it's working, if I don't have Wi-Fi, then push through.
Hi, I'm on the website. Yeah, I just need to Thank you so much.
You're not missing an exam, right?
I don't know.
So you said so far that anything that's on the clicker doesn't count. Okay, since I had 5 absences, so
Everyone has 5 hours.
okay, that's what I